start by just recalling what we were doing last time, so we can kind of pick up the thread. So we started, right, by making up some typing rules for the lambda calculus, right? So we started with the lambda calculus, which doesn't have any types. You can do whatever the heck you want. Then we said, well, let's see if we can make up some types so that we only do things with lambda calculus terms that make sense. And so this is what we came up with. For example, if T1 is a function from alpha to beta, then T2 had better have type alpha so that it can be an argument. And then if you apply T1 to T2, you'll get a beta as alpha, right? Said, right, if you have a variable, you have to know, you have to already assume what it is from your context. And if you have a lambda, say, well, if we assume that x has type alpha, if under that extra assumption we can say that t has type beta, then we can make this lambda that's a function from alpha to beta, right? So x is the input, which is alpha, and then t can use x, it'll give us a beta. So then, I think I erased all the orange things, and then we noticed that what was left was we'd already seen, right? It was the rules for propositional logic, well, specifically for implication, right? For implication, introduction, and elimination. And then I was starting to explain this link between propositional logic and the lambda calculus. So the way we think of these, the orange things are lambda calculus terms, but we can also think of them as proofs. So the orange things kind of encode what was the structure of the proof, and the type of the thing we can read as a proposition, right? So, so today I want to expand a little bit more on what the heck is going on, and also, we've only done implication because that's all. We only had a type for functions that correspond to implication. So, since we already know about, we have other logical things like and or. And so the question is, do those correspond nicely to things, to programming language things? And yes, of course they do. So we're going to look at that today. So, all right, that was just, now if I go back to here. So this whole phenomenon is called the Curry-Howard Isomorphism, or the Curry-Howard correspondence. It's also sometimes called the Curry-Howard lambda isomorphism because we'll see that the Curry-Howard part, it's named for two mathematicians, and I don't remember off the top of my head enough of the history to give a coherent account, but anyway, it turns out there's like a third thing having to do with category theory that also corresponds. We actually have these three things, like programming, proving stuff, and also category theory stuff that all correspond. We're not going to talk about category theory in this class. It's very cool. I wish I could, but we're not going to. That's what the Lambeck part is. We're not going to talk about that. But, the basic idea is types correspond to propositions, right? And then terms having those types correspond to proofs. Okay? That's the part of the correspondence. Right? And it turns out this is even way deeper than just thinking about lambda calculus specifically. So, there's lots of examples of where if you have a certain kind of programming language, it corresponds to a certain sort of logic, or vice versa, right? If you come up with some kind of logic, like, oh, I have this logic and it's got these things in it and these extra features and stuff, you can fruitfully ask, what is the programming language that kind of corresponds to this, where the types of the language are the propositions in my logic, and programs in that language would be proofs in my logic. We're only going to look at we personally, no, that's not true. We're starting by looking at the simply typed lambda calculus, but when we talk about sort of the language AGDA, I mean, that has yet another, it's really just an extension of that. So, and we've seen a few things that we can put on either side. So, like, for example, we saw that over here, functions, or function types, corresponds to implication. Right? Because, how do you prove an implication? You prove an implication by saying, you know, suppose this, then that. Or you could think of it as, if I want to prove an implication, basically I'm telling you, I'm willing to, if you tell me why A is true, then I will explain to you, you know, starting from that, I will explain to you why B is true, right? That's A implies B. Okay, we'll come back to this list and we're gonna fill in a lot more things in this correspondence, but this is a good place to start. So actually, I'm just gonna start a new page. So we can come back to this page and like put more stuff on there. But let's recall some of the rules we had for. I'll make a table. We had. Yes. Elimination rules. And what we can do and here. Or it already implies. Maybe we'll get around to talking about top and bottom. Might as well. Not quite as important in terms of programming, but still. Okay. So for introduction, for and, right? How do you prove an and? So if I had gamma shows, I guess I'm using like alphas and betas. Alpha and beta. Right? How do you prove? Oh, I need to leave space. Okay. I'm leaving space because ultimately we want to see if we can fill in something here that will be a kind of lambda calculus-y thing, some kind of programming thing that will count as a proof of this, right? But for now, I'm just saying, okay, just what were the logical rules? So, well, how do you show alpha and beta? You have to show alpha and you have to show beta, right? So this was just a rule that said, if you can prove alpha and if you can prove beta, then you can prove alpha and beta, right? And then for elimination, we had two rules, right? One that said, if you know an and, then you can ignore one or the other and just conclude, you know, if I know alpha and beta, then I know alpha. I can ignore the and part if I want. So we had one rule that said, this. Another rule that said, so, all right, before we, yeah, we're not going to have space for these. We're already like running into. So let's just think about this for a little bit and think about what might this correspond to in terms of, so number one, we need to think of this as a type, right? So, like if alpha is a type and beta is a type, we need to be able to think of, because propositions are supposed to correspond to types, right? And so I need to be able to interpret this as some kind of type. And then I need to fill in some, you know, some things here that kind of make sense. So, well, how do you prove something of type, or you know, this proposition alpha and beta? I mean, it's pretty simple, right? You have to prove alpha, and you have to prove beta. You have to have both, right? So, if, if like T1 is a proof of alpha and T2 is a proof of beta, if I want to have something that represents the proof of alpha and beta, then I just want both of those, right? Plain and simple, like what counts as a proof of, how would you convince me that alpha and beta is true? You have to separately convince me of both things, right? And so, this is what we're going to put. And so, this and thing, what type does that correspond to? It just corresponds to a pair type. Like in Haskell, we would write it with, with parentheses and a comma. So this is like alpha. Okay, so and does that make sense so far? Why and corresponds to pair, or is it also called a product type? And you'll sometimes see, instead of writing like Haskell writes parentheses alpha comma beta, you'll also sometimes see people write like alpha times beta. And the reason is pretty simple. If think about how many elements are in, if I have like 5 things in the type alpha and 7 things in the type beta, how many things are there in the type alpha comma beta? Well, there's 35, because I've got like 5 possibilities for the first one and 7 possibilities for the second one. You put them in like a big table, like a multiplication table, right? It's the Cartesian product, if you think in terms of set theory. So, okay. So what should go down here? So if I've got reading this as in terms of propositions, this says if I have T, which is a proof of alpha and beta. Reading it in terms of programming, this says if I have T, which has type, alpha comma beta, right? Then again, like in terms of proofs, this says what should I put here that counts as a proof of alpha? In terms of programs, it says, well, if I have something of type alpha comma beta, how would I get an alpha? What do you think? Like in Haskell, if you had something of type A comma B, and you wanted an A, what would you do?
Call first on it.
Call first on it, exactly. That's exactly what we put here. So right, the fact that from A and B we know A corresponds to the fact that if we have a pair, we can throw away the second part and just keep the first part. Okay, and then obviously this should be. Okay, cool. So actually we can go back and fill in this pair or product type corresponds to and. Okay. Let's go about OR. So OR is a little, maybe slightly trickier to think about, but in the end, not too complicated. Let's remind ourselves what rules we have. So the intro is actually pretty simple. If I want to prove A or B, right, one way I could do that is just by proving A. And then there's another rule that says, well, I could also just do it by proving B. So I'm going to have one rule that says, and one over here that says, we can prove alpha or beta. And then also, if I assume alpha, I can prove gamma, or, I mean, also, if I instead assume beta, then I can also prove gamma. This is, I can prove alpha or beta, and also, no matter which of those I assume, I can prove gamma. Then this just lets me say, gamma. And I'm going to leave a lot of space here. Let's see why. This one is a little complicated because of the fact that we have to introduce this extra thing gamma to talk about how we use it, right? Because, yeah, that's just kind of how it works. But, okay. So, any ideas or any thoughts? If I, again, thinking about what kind of programming thing would correspond to this. So if I want a proof of alpha or beta, right, then I'm willing to accept one of two things. I'm either willing to accept a proof of alpha, or I'm willing to accept a proof of beta. And I will note actually that this is one point where the logic we're using is something called constructive logic. I don't know if I mentioned this before. So not behaves slightly differently here than it does in what you're used to from like discrete math or something. So in what's so-called classical logic, which is what people use most of the time, there's kind of a third thing you might be willing to accept as a proof of alpha or beta, which is that you may be willing to accept kind of a proof by contradiction. This is, well, suppose not. You know, suppose alpha and beta are both false, then I can derive a contradiction. So one of them has to be true. Right? But that doesn't tell you which one. It just tells you like, well, they can't both be false. Right? In this kind of logic, we're not willing to accept that. So we're saying, no, if you're going to prove to me alpha or beta, then I want to actually know which one is true. I'm not willing to accept this like, well, they can't both be false. That was kind of a side thought. So any ideas what kind of, say, Haskell type that might correspond to? It actually occurs to me that maybe we somehow have not talked about like the specific Haskell type this corresponds to. I don't remember. We have or not. Well, in general, right, we've seen this idea of like, if I have a data type, it could be, you know, if I want it to be like one of two possible things, I can have two constructors, right? It's like, well, it could either be, you know, like a list. Well, it's either empty or it's a class. And depending on which it is, like it has different information in it. So you can imagine defining proofs of alpha or beta as a data type that has two constructors. One constructor that says, yeah, it's going to be, it's the first one, it's going to be alpha, and then it contains a proof of alpha. Another constructor that says, no, it's the second one, it's a proof of beta. So the Haskell type that corresponds to that most closely is something called, stop me if I talk about this, but I'm not sure I know. This is in the standard library. There's a type called either. The idea is that a value of type either AB is either an A or it's a B. And so there's two constructors, and it tells you which one it is. So there's a constructor called left, which contains an A, or put another way, like one way to construct an either AB is to say left and put an A in there. The other way to construct an either AB is to say right and put a B in it. Okay? Does that make sense? So if I was given an either AB, I can pattern match on it and have two cases. And say, well, if it's a left, then I get an A and I can do whatever I want with A. Or if it's right, I get a B and I can do whatever I want with A. So this is called a sum type. just like this is called a product type, the pairs. And if you think about it, just like, how many elements are there of a pair, the type of pairs, it's like how many, it's the size of A times the size of B. With the sum type, right, how many different values are there of type either A, B? Well, it's however many values are of type A plus however many values are of type B, right? There's either one or the other. So people sometimes write this as literally like with a plus. You'll see that also. That's not valid Haskell syntax, but so we'll say this equals either A alpha beta. Okay. And then, all right, well then what should we fill in here? So if I have, if T is a proof of alpha, then left T is going to be a proof of alpha or beta, right? Because I'm saying, look, which one is it? Do you have a proof of alpha or beta? Well, it's the left one, it's alpha, and here it is. There's the proof of alpha. Right? Or, of course, this one's going to be right. Okay, and then this one looks a little scary. So let's think about what's going on here from kind of a programming point of view. Right, this says, look, you have a proof of alpha or beta. So it's got to be one of those two things. It's either a proof of alpha or it's a proof of beta. We don't know which yet. It's one of them. And this is saying, okay, well, you have to be prepared for whichever one it is. And you have to say what to do in either case. Right? So if it's an alpha, you have to say how you're going to get your gamma from that. Or if it's a beta, you also have to say how you're going to get your gamma. Right? You have to be prepared to use either one, and then use them however you want to get a gamma. And then we say, all right, well, if you've given all of that, then you can get a gamma by taking this thing and kind of running it through whichever one of these two things applies. Right? So this is just like doing a case. We're doing pattern matching. Right? We say, let's pattern match on this thing and see which it is. And depending which it is, we're going to either choose to do this or we're going to choose to do that. Okay? So that's exactly what this corresponds to in programming terms. So if I have, let's say T is this proof of alpha or beta. And then we're going to call this, we're just going to say like, okay, X. I'll call it like, we'll call them L and R. What about that? Alpha. Okay, so then this is going to be, I've got some, I'll call this like C1 for like case 1. This is going to be like C2, case 2. And then what goes down here? Like what is the actual term that kind of corresponds to this whole thing? It's basically like a case expression. So it's like saying case have we seen case syntax in Haskell? No? No, we're not. Okay. Well, I'll write it like this already. It'd be kind of like defining a function that says f of left L equals C1, f of right R equals C2. Okay. Except I don't actually define the name of a function. It's just like an expression that does the pattern. I'll write it down here the way that we've already written. And this is valid Haskell syntax. You can say case. This is basically if you want to do pattern matching, but you don't want to define a helper function to do it for you. you can just do it as a case expression. It just says, hey, here's a thing, pattern match on this, and then choose which thing matches and do that. So I would say case, oh, I guess I'd have to say like, to make this work, I have to say like define that thing and then do F of C. Something like that. I have to actually use the T. I was like, wait, I didn't use T in my definition at all. That's not good. Right, it'd be like defining this helper function and then calling it on T. But I can write it directly by saying case T of, and then I would say like, well, if it's left L, then C1. Otherwise, if it's right R, then C2. Okay, so you could write it this way as well. There's something strange about the fact that like all the rules and the syntax for what corresponds to it is so simple except this one. This one you need kind of like complicated syntax to express the fact that you're doing pattern matching or something. But there's something a little asymmetric about it. I haven't quite wrapped my brain around why. But whatever. That's what it is. Okay? So, right, big picture. And and or, which are these very fundamental logical operations, correspond in programming terms to very fundamental programming things, right? So product types or pairing, I mean like every programming language has ways of putting multiple pieces of data together, into one thing, and then like getting out pieces of the data that you put together, right? Think about like making a Java class. You can have multiple like fields in the class, and then you can like project them out. So just give me like, my object dot X or dot Y. Haskell has, actual pair type, etc. Some types, not all languages provide this as like a primitive thing. So, Haskell definitely does. Rust does. Like Java and Python, for example, do not. There's actually no way in Java and Python, no direct way, to say I'm making a class or a data type, and it's either this or this. However, just the idea of like pattern matching, I mean and again, some languages don't give you pattern matching as such, but at least they give you if, right? Which is kind of like the ultimate form of pattern matching, where you say I have a true or false, and I can decide whether to do this or this based on that. Because you can define Booleans as like, a data type with two constructors, and then pattern matching on that is basically what if is. So think of it like a lot of languages have a very impoverished form of some types and a very impoverished form of case, but it's like just enough to let you do stuff. So you can kind of pretend that you have girls who don't. But every programming language has these things kind of in some way. Okay. Let's see really quick what we can do. So remember we had the rule. We had this rule. It says you can always, you don't need any assumptions, you can prove top. Does that correspond to like true? And then we had an elimination rule. It said if you can prove bottom, then you can prove anything you want, because this is like getting a contradiction, right? Bottom kind of corresponds to false. So what do these correspond to in programming terms? Well, so this is like you can always make a value of this type. You don't need any information to do that. This is like, so in Haskell, C corresponds to the unit type, which is kind of like data unit equals unit, like there's only one value of that type called unit. So having a value of type unit is totally uninformative because there's only one possible value it could be. It doesn't tell you anything. Right? So, it's supposed to be orange. And then bottom corresponds to, in Haskell it's called void. This would be like having data void equals nothing. Or I should say like, you actually write it as data unit where unit is something. And data void where, that's it, nothing. So this void is the type with no constructors, which sounds kind of useless, and it is useless by itself. But it can be useful for expressing other concepts in terms of, because we can think of it as corresponding to bottom or corresponding to false. Right? So there's no constructors for it. There's no possible way to construct a value of type void. It's still a valid type. There just happen to be zero values of that type. Okay?
So void is built into the standard library?
It is. There's a library called data, a module called data.void that defines void. And it defines it like that. I mean, why not? Like I said, it's not very useful by itself. It can be useful in certain situations. Well, it's a similar idea to like, so for example, the Haskell standard library defines the ID function, which just returned its input, right? Like ID x equals x. Why would it define that, right? That doesn't seem useful at all. If I have x, I don't need to call ID on it. Well, one reason it's useful is because you might have a function that takes, a function as input. Maybe it takes several arguments, one of which is a function, and you're like, well, I want to use this function, but I actually, in this part of what it does, I don't want it to do anything. So I can do that by providing ID as one of its arguments, right? If I actually want, like, just the default here, I don't want it to do anything. Void is kind of useful. It's similar. You could have a data type that takes several parameters that are types, and you say, well, here I actually don't want to use this one at all. So I can put void in there, and that kind of shows that I'm not using it. I'm being a little hand-wavy, but I'm saying the point is, it's not useful by itself, but it's useful in combination with other things. In any case, the idea is some languages would have things like, maybe like, often it's called like abort. Right? If you manage to make a value of type void, it means something has gone wrong. And so there's like some built-in thing called abort that just like crashes the program. Haskell has a function called error that works kind of similarly to this. Anyway, don't worry about those as much. These are important ones. So we can go back here and we can fill in numerous things like, type. Corresponds to or. We can list more things in here. So, for example, if terms correspond to proofs, right? Then, like, for example, something like a helper function. Right? If a helper function is like not the main thing I care about, right? It's like it's just helping me to accomplish something else. What does that correspond to in proof land? Well, that's usually what people mean by a lemma. So a lemma is like a little thing you prove, but you don't really care about it by itself. You're just using it to help you prove something else, right? And you'll see when we write AGDA programs, literally, if you want to prove a lemma, the way you do that is you make a helper function. Literally, they are the same thing. What else? There's something else. We will find more things to fill in here Then we learn AGA, would be a lot more, but that's what we know right now. Let's do some examples. Examples are always good, right? Where should we do it? So there's a lot of things we could do with this. So I don't mean to imply by this example that this is the one way to think about this or the one thing to do with it. But as one example, right, we could, if we say something like, prove that, A and A implies C implies A and B implies C. Okay? So if I had asked you this before, right, maybe on one of the previous homeworks, I might have been wanting you to make like a proof tree that kind of like constructed a proof of this using the rules, right? But now that we know that lambda calculus terms, or Haskell terms, if you think about in terms of lambda, pairs, either, etc., the programs correspond to proofs. One way I can prove this is by giving a program that has the right type that matches. Okay. So one way we can do this is by giving a program that has the corresponding type. Okay. And I can't just write any Haskell program I want. Right? I'm not allowed to use Haskell features that don't correspond to things that we've talked about that correspond to these logical things. But I can use pairs, I can use first, second, I can use lambdas, and I can use left and right, and I can use case, or I can do pattern matching. Right? So for example, I can't use recursion. Okay, recursion is out, and we'll talk more about why. I can't use int. That doesn't, we have to talk about, that doesn't correspond to anything in this logic. So, well, maybe I can say, all right, well, it's going to need to take, f, and we'll just write down what the type of f is. F is type A or C. And then I need to return a function A and B to C. Well, I can take another, so I can say lambda P, which has type A comma B. That's the same thing as and. And now what needs to go here? I need to put there something of type C. Any ideas? How can I get something of type C? I have f, which is an A to C function, and I have P, which is a pair of an A and B.
Would you do like F applied to left A?
F
Or
applied
left
to,
to P?
yeah, well, first, not left, yeah.
Or first, yeah.
Yeah. Yep, exactly. Good. So if we believe this correspondence between lambda calculus and propositional logic, then this actually is a valid proof as well. And if we, I'm not going to do this, but if we constructed the whole proof tree that we would have done before, and we filled in all of the little, all the terms, so we now have these proof trees, but they've got these extra orange things in them, right? If we filled in all the orange things, we would get this. This is what we would have at the bottom. As the last step, we would have this thing. So this lambda calculus term itself is kind of encoding the whole proof tree in a much more compact format, and a format that gives us much better intuition as to what is going on, right? Because really this is saying, okay, look, if you have this implication, then all right, we're going to call that f. And then, all right, we're going to suppose that we have a proof of A and B. I'm going to call that P. And then how am I going to get my proof of C? Well, because I know P, because that's a proof of A and B, I can just ignore the B part and get the A out, right? That's a proof of A. And now I have this implication from A to C, so I can say, well, since A and C, and if I know A, then I know C. Well, that just corresponds to applying the function f, that thing, right? So again, we can think of this kind of on two different levels, as a program or as describing kind of a procedure for getting a proof. We'll do one more example. So, prove that, let's see, A or B implies C and B implies C. This might have been one of the ones that we've done on a previous homework, I'm not sure. One of the like level 2 things on one of the previous homeworks kind of pointed out how the function, the implication arrow kind of behaves like, if we treat it like an exponent, then it corresponds to exponent rules. So this is like C to the A plus B is C to the A times C to the B. Which is why I come up with this so quickly. Because it's oh right, that's my first. So what would a proof of this look like? Well, I need to take, we'll call this F. So lambda F. And I'll say A plus B goes C. Or I could write either AB if I wanted. Okay, and now, well, I need to return something that corresponds to A implies C and B implies C. So and corresponds to pairs, so I need to return some kind of pair. So I could just put this in here like this. Okay, what goes in here? What goes in here is a proof of A implies C, or equivalently a function of type A arrow C.
So do left there, and do left of to get the A value from
Yeah,
the
so I
board,
need to
you
say
would
like
call left of the A plus or A or B.
Yeah, so I definitely want to use F somehow. I have to get my C. So, but I could start by saying lambda little a, which is A, and then yeah, I can get a C out of F if I put an A plus B in. I don't have an A plus B, I have an A. But if I say left A, that'll be something of type A plus B. Right? So I can say F. I'm putting this first direction. Left A, comma. All right, and then what needs to go over here? This is going to be a B arrow C. This is going to be something like lambda B, F. Right. And again, if you made this into a tree, you would see a proof tree. You would see the same thing, where you would first kind of do the lambda intro rule, and then you do like the and intro rule, and it would like split into two subtrees. One subtree would give you this part, and one subtree would give you this part. And you would do more like implication intro rules for this and this. If you make out the whole tree, and maybe I'll find one and we can look at the correspondence next time. But if you squint, you'll kind of see that they have the same structure. So this is the basis for, as I mentioned, the ability to have computer programs that can, where you can formally write down proofs and have the computer check your proof. and even to have the computer like find parts of the proof for you. And so what people have done is, number one, we've seen the simply typed lambda calculus corresponds to kind of, simply typed lambda calculus with sum and product types corresponds to sort of first order propositional logic. But you can kick both of those up a notch and have like a much more complicated kind of logic that corresponds to a more complicated programming language, still based on the lambda calculus and propositional logic. But that actually let you state and prove much more interesting things. Because right now we're kind of limited to proving, like it's stuff that ancient Greeks would have talked about, like, if Aristotle ate oatmeal and Aristotle is a man, then, and many oatmeal, whatever. It's just like, not actually that exciting. Right? We can't say anything, for example, about, prime numbers or about, really anything that that might be more interesting to talk about. So, but these sort of like more complex languages will give us that. And so next time we're going to start learning Agda, which is a different programming language. We're going to come back to Haskell later in the semester, but we're going to kind of do a little interlude learning Agda. And Agda is very similar to Haskell, except it's kind of like the type system is jacked up on steroids. So if you thought Haskell's type system was crazy, Agda's is even cooler. But Agda actually lets us like prove stuff. So we can use it as a programming language or as like a proof language. So we can write down interesting statements of logic and then prove them by basically writing Agda papers. And the Agda type checker will like check and say, yes, this is valid, or no, it's not. And it actually even kind of helps us keep track of, okay, what do you have left to prove? Here's what needs to go in this hole, et cetera, et cetera. So it's kind of fun. It's like a little video game. You're like trying to construct these proofs, and it's like telling you kind of what you have to do with these stuff. So that's kind of where we're going with this. Any questions? All right. See you all on Wednesday.